The topic of this video is buffers. In this video, we're going to see a short little demo of a buffer. We're going to talk about what a buffer is, how we determine the pH of a buffer when we're given exact components of our buffer, and then number 3, if we're not given exact information of the buffer, how can we estimate the pH range it will maintain? So first, we're going to take a look at a quick demo of a buffer that you would encounter in your lives. Buffers are really important to our daily lives. Our body itself contains buffers. We will learn in class about buffers in our blood that allows our body to maintain a certain pH. The buffer that we're going to look at in our demo is one that's found in an antacid, in an Alka-Seltzer tablet.
For this demo, we are going to use a buffer that you may take if you have an upset stomach, Alka-Seltzer. So if you look at the back of an Alka-Seltzer tablet, I don't know if I can focus on this very well. If you look at the back of the Alka-Seltzer tablet, it will tell you that there's citric acid present in the tablet as well as sodium bicarbonate. Citric acid obviously is an acid and sodium bicarbonate is a base. So this meets the criteria of a buffer. It contains both acid and base components. So what I'm going to do is I'm going to take this antacid and I'm just going to add it to some water that has a universal indicator in here. So you'll notice it's green to start because water is neutral. I'm going to go ahead and put my Alka-Seltzer tablet in there, and as it reacts with the water, we're going to see that it will change the indicator to kind of like a pink color. That's because it's going to maintain a pH that an acidic pH. Obviously, we take this for our stomach, and there's hydrochloric acid in our stomach, so we want our stomach to be at a lower pH value. So I'm just going to let this react for a moment. What's going on is as this acid bubbles, or I'm sorry, as this tablet bubbles, it is dissociating, it's breaking up. My citric acid and my sodium bicarbonate are dissolving into my solution. The sodium bicarbonate can also produce carbon dioxide bubbles, and that's what we're kind of seeing as this reacts. But ultimately, we'll get this buffer to stabilize out and to maintain this like pinky orange color. So all I'm going to do is take an acid and a base, and I'm just going to add it to this buffer. So I'm going to start with a base. You would expect to see the biggest change when I add a base, knowing that this is already acidic. So I'm just going to add 10 drops of my base. And if you notice, the color of my solution really did not change. If it had truly changed as I added the base, it would have turned like a blue or a purple color. Sodium hydroxide in the presence of that universal indicator would again be a purple or a very dark blue. I'm going to do the same thing with my hydrochloric acid. So I'm going to take a couple drops of my hydrochloric acid. You can notice as it is dropped into my solution, there's really no color change with my my antacid and water. So this buffer is maintaining a specific pH. And again, that is really the point of a buffer. A buffer by definition must contain an acid and a base to resist a change in pH. So there's something in that buffer that will react with the base that I add to neutralize it, and something in that buffer to react with the acid that I add to neutralize it.
So as we saw from that demo, a buffer is something that's going to resist a change in pH. So there is something in that buffer that will react with any acid that I add to it to neutralize it, or any base that I add to that buffer, and it will also react to neutralize it. So if you think about it, if it can neutralize an acid and it can also neutralize a base, that means a buffer must contain a component that acts like an acid, so it can neutralize that base, and a component that acts like a base, so it can neutralize any acid I add. So a buffer must consist of weak conjugate acid-base pairs. Now this weak component is really important. We will see a buffer example that is composed of hydrofluoric acid and sodium fluoride. So these are actually conjugate acid-base pairs. HF, the conjugate of it, it's an acid, so after it donates its hydrogen, it will turn into fluoride. So these are conjugates. If I had tried to make a buffer of HCl and NaCl, I would actually not have a buffer. I would not have conjugate acid-base pairs. Because I know that HCl is a strong acid, it actually doesn't stay together as hydrochloric acid. It will dissociate immediately into Cl. So this cannot be a buffer because I would only have Cl minus present. I would not have conjugate acid and its base. So I would not have a component that could react with an acid and also react with a base. So we know that the conjugate acid, in this case my hydrofluoric acid, could neutralize my base, whereas the conjugate base, in this case my F minus, can neutralize any acids that I add. So my example of the buffer is something that's composed of 0.200 moles of hydrofluoric acid. So this would be my conjugate acid. And 0.100 moles of sodium fluoride. This would be my conjugate base. Now, if you are confused as to how I was able to identify the acid versus the base, remember back in Regents Chem where we compared two sides of a reaction, if we had HF on one side and F minus on the other, and we were able to link up the conjugates, they would be the most similar in formula. Well, the one that had the greater number of H's, in this case that's my HF, so this one contains a greater number of hydrogen, that is always going to be my acid, okay? Because acids by definition, by Bronsted-Lowry definition, are proton donors. So it only makes sense that the conjugate that has more H's is going to be better at donating its hydrogen. Whereas the one that has the lower number, or the less H plus, is going to be my conjugate base. Now, the sodium in this case is just a spectator. I can't actually just get F minus fluoride ions. I always have to get it with another metal as a salt, and then we dissolve it in water. The sodium is present, but it doesn't participate in any reaction. So I know I have these conjugate pairs where the weak acid can react with any base that I add to resist a change in pH, and the conjugate weak base can also react with any acid I add now to resist a change in pH. So the benefit of these buffers is now we can maintain a specific pH. So this is really important to our bodies, which have to maintain homeostasis. So we have buffers in our blood, for example, that are going to maintain a specific pH so that our blood doesn't become toxic or doesn't reach a pH outside of the range that our body needs it to maintain. So one of the things that you're going to be asked to do is to write reactions that will show how that buffer will resist a change in pH. Essentially, how it's going to neutralize any acid or any base that I add. So I see, write a reaction to show how the buffer will resist a change in pH when hydrochloric acid is added. So HCl I know is an acid. And I also know that a base is going to neutralize that acid. So that means that my base component, my NaF, is going to be the component of the buffer that is going to neutralize any of the acid that I add. So again, if I add acid, I'm looking at that conjugate base in my buffer. And then this is just like any neutralization reaction we write in class. It's just like a double replacement reaction. So my H and my F are going to combine to make hydrofluoric acid, and my Na and my Cl are going to combine to make NaCl. Now I could also write this, I could break it up and eliminate spectator ions, and if I were to do that, I would get H plus Cl minus, that's a strong acid, so it will dissociate. Na plus F minus, that's a soluble salt, so it will dissociate. Makes HF, that's a weak acid, will not dissociate, plus Na plus Cl minus, again a soluble salt. So my Na's cross out and my Cl's cross out, so I end up getting the equilibrium that my weak acid would have had if it was just its only component. Okay? So I can see that, again, one of the components of my buffer, in this case of the conjugate base, can react with any acid that I add. As long as there is enough of that conjugate base, it can fully neutralize that hydrochloric acid. So in my next example, now I'm going to not add, now I'm not going to add an acid, I'm going to add a base. And in this example, it says I'm adding sodium hydroxide. So I'm just going to go to a blank screen. Sodium hydroxide is a base. So what will neutralize a base? Well, I need the component of the buffer that was the acid. And if we look back, hydrofluoric acid was the component of my buffer that met this criteria. So this is just a simple neutralization reaction. Na and F are going to pair up, and then my H and my OH are going to pair up to make water. Again, I can simplify this and write it as a net ionic sodium hydroxide strong base. So it's going to break up. Hydrofluoric acid, weak acid. It's going to stay together. NaF, strong, soluble salt, so it will break up. And then water, liquid, will not dissociate. So if I look, oops, I crossed out the wrong thing. If I look, my Na plus is a spectator in this case. So I'm left with my base being consumed by my hydrofluoric acid, which forms my conjugate base and my water. And assuming there is enough of this acid to fully react with my base, then I will maintain relatively the same pH that I started with. So I mentioned that assuming there's enough of that conjugate, I will maintain a pH. There is a limitation to our buffers. That's referred to as a buffer capacity. The amount of an acid or base that can be added to the volume of a buffer before that solution starts to change its pH significantly is my buffer capacity. So essentially what that means is my buffer, which again contains conjugate, acid, and base pairs, there has to be enough of those conjugate acids and base pairs to fully react with any base that I add or any acid that I add. All right, so this graph right here is just showing this is the range, okay, this is the amount of my conjugates that I have enough of to fully neutralize any acid or base present. If I add my hydrochloric acid, enough of it so that I completely consume all of my conjugate base, I no longer get this reaction. All I have is some additional hydrochloric acid being added to my system, so my pH is going to drastically drop. All right. So again, there are some limitations to our buffers. They can only neutralize so much. Obviously, the more we have of those conjugates, the better it's going to do. As you add more and more acid, the longer it's going to resist the change in pH. But it's not going to last forever. So the second topic that we need to be able to do is to determine the pH of a buffer. So I'm going to use the same example. I have a buffer that's prepared by dissolving 0.2 moles of HF, so 0.2 moles of HF to make a 1 liter solution. So we said that's 0.200 molar. And I'm just going to use F minus for sodium fluoride because I know sodium is a spectator. I'm dissolving 0.100 moles of that per 1 liter. So that means I have a 0.100 molar solution of my fluoride. I want to find the pH, and I'm given a Ka value. So Ka stands for acid. I know that Ka's usually tell me I'm going to set up racea. I'm going to do just that to determine the pH of my buffer, kind of like we do with weak acids or weak bases. So to write my reaction, I have to look at which of these two components, the HF or the F minus, is my acid, because I'm given a Ka, so I want the acid to be reacting. Well, my hydrofluoric acid is, of course, my acid. I'm going to react it with water. And I know acid's job, or according to the Bronsted-Lowry theory, acids will donate a hydrogen. So I'm going to get H3O plus F minus. I also know that I have initial concentrations of both my HF, and that is 0.200 molar. Water doesn't have a concentration, it's a liquid. And I'm given a concentration of my fluoride, which is 0.100 big M. So this is a little funky because I'm starting with 2 amounts instead of 1. I'm not given any information on my H3O+, so I'm going to call that 0. Because there's a 0 here, I can't take from the product side. So this is minus X plus X plus X. E is the sum of I and C, 0.200 minus X, 0 plus X, 0.1 plus X. And now I'm trying to figure out if I want the pH of my buffer. I'm really interested in this H3O plus column. So I ultimately have to figure out what is the value of X. So I'm given a Ka, and that Ka is equal to the concentration of my products over the concentration of my reactants. I don't put water in my Ka because it's a liquid. So I can substitute in. H3O plus was X, F minus was 0.1 plus X, and then my HF is 0.200 minus X. And I know that whole thing is equal to my Ka. So that's 6.8 times 10 to the negative fourth. Now I can do my algebra here. I can throw this over 1. I can crisscross. I can cross multiply. I can move all my variables over to one side of the equal sign. I'm going to give you the end quadratic equation when I do all of that math. I get x squared plus 0.09932x minus 1.36 times 10 to the negative fourth equals 0. When I plug that into my quad program on my calculator, I get 0.00135 is my answer. That is the value of my X, which I can use to determine the pH, because pH is the negative log of my H plus concentration. So pH equals the negative log of 0.00135. My pH is going to equal 2.87. So what that means is if I add some acid to this buffer, it's going to stay around 2.87. It's going to stay around a pH of 3. So if I have a reaction that needs to take place at a pH of 3, it would be a really good idea for me to employ a buffer to make this reaction take place in the presence of this buffer. All right, to keep the pH around a 3. So that was kind of a long way to determine the pH. I'm going to show you a shortcut. This formula, the Henderson-Hasselbalch equation, is in your reference tables. It's pH equals the pKa plus the log of A minus over HA. So in this reaction, pKa, remember P means negative log, like pH is the negative log of H plus. pKa is the negative log of Ka. If I had a pKb, it would be the negative log of Kb. And this is defined in your reference tables. A minus, remember when we have brackets, that means concentration. So A minus is the molarity of my conjugate base. Remember the one with the least amount of H's is my base. And then HA is the molarity of my conjugate acid. So what this allows me to do is bypass that whole Ricea table. I'm going to use the same example that I just did and plug in my information into this Henderson-Hasselbalch equation. So I know the Henderson-Hasselbalch equation is pH equals the pKa plus the log of A minus all over HA. So I need to know three things to get my pH. I need to know my Ka, which I'm given. I need to know the concentration of A minus, so that was my F minus in this case. And I need to know the concentration of my HA. That's my acid or my HF in this case. So this would be my HA concentration. So I have all the information. I just need to plug it in. pH equals, the P stands for negative log of my Ka, 6.8 times 10 to the negative fourth, plus the log of A minus concentration, so that was 0.100 big M, all over the concentration of the conjugate acid, so that was 0.200 big M. So I plug this all into my calculator, and when I do that, I get 2.87. If we compare, that is the exact same pH I got when I use the Ricea to get to my answer. So this is kind of a shortcut, much easier, much less algebra and work to get to my pH. This is also going to allow us to estimate the pH that a buffer will maintain. So that's our last topic. To estimate the pH range for a buffer, we can use the Ka or the Kb. So if we go back to that Henderson-Hasselbalch equation, I'm really just bypassing the amount of conjugate acid and base pairs. So I'm saying pH equals pKa roughly, because this is going to be a relatively small number. So, and this is just for the purpose of estimating. So what that means is the pH range is approximately going to equal the pKa. So if I look at my buffer, my HFF minus buffer, that has a Ka value of 6.8 times 10 to the negative fourth, if I'm trying to roughly estimate the pH that it will maintain, I can just do the negative log of that Ka. I get 3.17, which means it's going to maintain a pH range of around 3. Now, obviously, this pH range, the exact pH of my buffer, is dependent on the molarities of the conjugate acid-base pairs, but this is going to allow me to estimate quickly. So if I'm given a multiple choice question that's asking me about buffers, I can look at my Ka and roughly estimate what pH it will maintain. So I would look at my exponent, which is -4. I would think it would maintain an acidic pH range because that -4 would be close to a 4 in my pH. So this is just a way to eyeball it. Again, you need to know 3 things about buffers. What a buffer is, okay, you need to be able to write neutralization reactions for the conjugate acid and base, neutralizing any acid or base added. You need to be able to determine the pH of a buffer, and I'm just going to assume that you are going to prefer to use this Henderson-Hasselbalch equation. And you also need to be able to pick from a list an appropriate buffer to maintain a specific pH. So not necessarily do a bunch of math, but to use this quick little shortcut to figure out what pH range each of those buffers could